In the last lesson, we learnt about the development of the modern theory of acids and bases, the Lowry-Bronsted theory. Acids are proton donors. Bases are proton acceptors. We will move on now to learning about acid-base pairs. Acids and bases exist as conjugate acid-base pairs. The term conjugate comes from Latin. It means joined together, and it refers in particular to things which exist in pairs. Lowry-Bronsted acids and bases always exist in pairs. Every time an acid donates a proton, it forms a conjugate base. Hydrogen chloride gas donates a hydrogen ion to a water molecule to form a hydronium ion. Hydrogen chloride gas is an acid because it donates a proton. The water molecule is a base because it accepts the proton. When hydrogen chloride donates its proton, a chloride ion is formed. The chloride ion can react with the hydronium ion to push the equilibrium backwards, forming hydrogen chloride gas and water. The chloride ion would then be reacting as a base. Hydrogen chloride and the chloride ion act as an acid-base pair. When hydrogen chloride acts as an acid by donating its proton, it forms the chloride ion, which is its conjugate base. Together, hydrogen chloride and the chloride ion form a conjugate acid-base pair. However, there is more to come. Hydrogen chloride donates its proton to the water molecule. In this case, the water molecule acts as a base when it accepts a proton. That is the hydronium ion. Hydronium ions can donate protons. They are Lowry-Bronsted acids. The second conjugate acid-base pair is therefore the hydronium ion and the water molecule. We label the pairs as pair number 1 and pair number 2 respectively. Take note. The reactants on the left-hand side of the equation have an acid and a base from each of the two pairs, and similarly, the products on the right-hand side have an acid and a base from each of the pairs. Can you identify the conjugate acid-base pairs in this example? CH3COOH loses its H+ ion and releases the anion CH3COO. Therefore, we will name CH3COOH as acid 1 because it gave away its proton, and its conjugate base is the CH3COO ethanoate ion. The hydroxide ion accepted the proton to make a water molecule. The hydroxide ion originated from the dissociation of NaOH in water. Sodium hydroxide is therefore a proton acceptor, base 2 in this reaction, and the product that is formed, the water molecule, is acid 2. Another example to practice. When you open a bottle of concentrated hydrochloric acid, hydrogen chloride gas escapes. Similarly, when a bottle of highly concentrated ammonia solution is opened, fumes of pungent ammonia escape into the air. Hydrogen chloride and ammonia are both colorless gases. They each have their characteristic odors, one with a sharp acidic flavor and the other with its sharp pungent smell. These two gases react spontaneously when they come into contact. They produce white clouds of ammonium chloride. The equation shows the reaction between ammonia and hydrogen chloride gas. Identify the conjugate acid-base pairs. Ammonia gas NH3 accepts a proton to form the ammonium ion NH4+. Bases are proton acceptors. Therefore, ammonia gas acts as a base in this reaction. The ammonium ion NH4+ is the conjugate acid of ammonia gas. We will label this conjugate acid-base pair as base 1 and acid 1. Hydrogen chloride gas donates its proton to ammonia and releases its chloride ion. Hydrogen chloride gas is acid 2 and the chloride ion is its conjugate base, base 2. Note that water is not involved in this reaction. The Bronsted-Lowry theory extends Arrhenius's theory to include any reaction which involves an exchange of protons as an acid-base reaction. Now, let's see if you can predict the formula of the conjugate base of each of the following substances. Work out the conjugate base of carbonic acid when it donates one proton. Similarly, the conjugate base of phosphoric acid when it donates one proton. What is the conjugate base of the hydrogen sulfate ion? And the conjugate base of water? Now, let's work the opposite way around. What is the conjugate acid of the following bases? The bromide ion accepts a proton to produce hydrogen bromide. And what about the conjugate acid of carbonate ion? The conjugate acid of the hydroxide ion? Here is a list of typical Lowry-Bronsted acids and their conjugate bases. First of all, notice that these substances can be positive or negative ions or neutral molecules. Also notice that some substances can react as acids and as bases. Water appears as a base and as an acid. So, does the hydroxide ion appear as both a base and as an acid? Substances which can act as a base and as an acid when reacting are called amphiprotic or amphoteric substances. Let's highlight the amphiprotic substances in this table. Water is the perfect example of amphiprotic behavior because it simultaneously acts as an acid and a base when it forms the hydronium ion H3O+. And the hydroxide ion OH-. The process of water acting simultaneously as an acid and a base in the same reaction is called autoprotolysis. Autoprotolysis is defined as a proton transfer reaction between two identical molecules, usually a solvent, one acting as a Bronsted-Lowry acid and the other as a Bronsted-Lowry base. Pure water molecules are aqueous solutions of water molecules self-ionize. One molecule releases a proton which the other molecule accepts. This process is known as autoprotolysis. Autoprotolysis also takes place in liquid ammonia. Two ammonia molecules react with one another to form the ammonium cation NH4+ and the amine ion NH2-. Take a few moments to identify the conjugate acid-base pairs. The products of this reaction are the ammonium ion and the amine ion. The ammonium ion is formed by an ammonium molecule gaining a proton. Let's decide that the second ammonia molecule gains a proton, and let's link the ammonia molecule with the ammonium ion NH4+. Because it is the second ammonia molecule, we will call this the second acid-base pair. The ammonia molecule accepts the proton, therefore it is base 2 and the ammonia ion is acid 2. There are two ways to proceed from this point onwards. Firstly, we know that if the second ammonia molecule is a base, then the first ammonia molecule must be an acid. Acid-base reactions always require an acid to react with a base. The other way to work out which is an acid and a base is to compare the two substances, NH3, ammonia, and NH2, the amine radical or ion. How does ammonia manage to produce NH2 ions? It loses an H+ ion. Therefore, ammonia molecules donate a proton to produce NH2 ions. Proton donors are acids. The first ammonia molecule is acid 1 and its conjugate base is NH2-. Acids are proton donors. Bases are proton acceptors. Acids have their conjugate bases. Bases have their conjugate acids. Let's move on to find out what makes a strong acid or a weak acid, and what is a strong base and a weak base.